Okay, so for today's video, we're going to follow up on the flip class video and continue with Taylor polynomials. Let's just recall we have seen before we can approximate with a tangent line approximation. So we've seen we can do this near A as long as we can evaluate f at A and its derivative at A by its tangent line. And so we write this now as P1 of x before we're using L of x for the linearization. But to go along with Taylor polynomials, we're going to use P1 of x for the first degree Taylor polynomial. So we have this as our tangent line approximation. So we saw in the flip class video we can use higher degree polynomials. To get better approximations. So we saw the formula we gave for this was for the nth degree Taylor polynomial. This is f of a plus f prime of a x minus a plus the second derivative over 2 x minus a squared. And then we keep going up, and so then we take the third derivative. So this is our notation for third derivative. We do x minus a cubed. And then we keep going up until, since this is the nth degree polynomial, we're going to go up to the nth power. This is the nth degree Taylor polynomial. Now the important property of this is that it matches the derivative of our function all the way up to the nth derivative. So we have, and this is what makes it a good approximation, notice if I plug a into this, all of the terms with degree 1 or higher will actually be 0, so this is just f of a. And then for any derivative, so let's just say the kth derivative, this will match the kth derivative of f. So it matches all of its derivatives, and this really makes it a good approximation. So we're not going to check this property in general, but let's just go ahead and check this for P3. Okay, so we'll check it satisfies these conditions. So recall here P3 of x then would be f of a plus f prime of a x minus a plus the second derivative over 2 x minus a squared plus the third derivative over 3 factorial x minus a cubed. So we can see if we go up here, we're just cutting off there at the 3 because we want the degree 3 polynomial. And so now let's check. So notice if we take P3 of a, all of these terms coming from here to here, those all have an a minus a in them. So those will all be 0. So this is just f of a. And now we'll take the derivative. So P3 prime of x. So the f of a is a constant, so that goes away. The derivative of f prime of a times x minus a is just f prime of a. And then I get, well, I bring the 2 down, so I get 2 f double prime of a over 2 x minus a plus 3 third derivative of a over 3 factorial x minus a. This should be squared now. And see, we can simplify this a bit, which isn't going to be so important for this calculation, but it will be for the next. And now notice that if I have 3 over 3 factorial, this is 3 over 3 times 2 times 1, which is 1 over 2 times 1, which is 1/2. So we get this. Now if we evaluate this at a, notice these terms here have an x minus a in them, so those will go away, and this just gives me f prime of a. We can start boxing in the things that we were trying to show were true. So we've got the first value and this first derivative equal. So let's continue. So let's take the second derivative. Now the f prime of a is a constant, so that will go away. The derivative of f double prime of a times x minus a is just f double prime of a. And then I'm going to get a 2 f2 times f3 of a over 2 x minus a. So this is f double prime of a plus the third derivative of a x minus a. No, this should be with an x, sorry. Just taking the derivative here, I haven't plugged anything in yet. And now when we evaluate this, notice we have an x minus a in this term, so this just becomes f double prime of a, just like we were expecting. And finally, we can check the third derivative. Show a 3 on it. Now the f double prime above here is a constant, so that will go away. And so then this derivative of this is just f3 of a, which is what we were expecting. So it's the same process for a general Taylor polynomial. It's just worth seeing it for P3 so you kind of see how those factorials are canceling out. But now let's go ahead and calculate some examples of Taylor polynomials. So we see how this works. So let's let our f of x be sine x. Let's let a be equal to 0. And let's compute P3 of x. So what we need is we can make some columns here. So this function is sine x. And then we evaluate it at 0. Well, sine of 0 is 0. Take the derivative and we get cosine. Evaluate this as 0 and we get 1. Since we're going up to degree 3 polynomial, we're going to need to take 3 derivatives. So this becomes minus sine. So this is again 0. And then finally the third derivative becomes minus cosine. So the third derivative at 0 is minus 1. So we just go ahead and do these computations up until we get to the degree we need, which in this case is 3. And now we just use our formula. So this is f of 0, so it's 0 plus 1 x minus 0 plus 0 over 2 x minus 0 squared plus minus 1 over 3 factorial x minus 0 cubed, which we can simplify as x minus x cubed over 3 factorial. So it turns out you can calculate, if you keep going up, it's going to continue in this pattern. So for example, you can check, say 7 of x is x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial, and so on. So there's no even terms for sine, which makes sense because it's an odd function, so you can't have even terms in there. Let's try another example. And it might be a good idea to stop the video and go ahead and open up Mathematica and plot some of these so you kind of see how the Taylor polynomials are approximating the function. So we saw some of this in the flip class video, but it's not a bad idea to stop and do that here as well. So in this case, let's look at 1 over 1 minus x. And again, let's take a to be 0. In this case, let's compute P4 of x. So again, let's make our table. So this is 1 over 1 minus 0, so this is just 1. So now we can think of this as 1 minus x to the negative 1. So this becomes a negative 1 times 1 over x, 1 minus x squared times the derivative of minus x, which is just negative 1. So this is 1 over 1 minus x squared. So f prime of 0. in this case is 1 again. Take the second derivative, now I'm going to get a 2 over 1 minus x cubed. So this is just 2. It's going to become 3 times 2 over 1 minus x to the fourth. Which we can also write as 3 factorial over 1 minus x to the fourth. And so f3 of 0 is 3 factorial. Finally, the fourth derivative, we want to go up to the fourth derivative because we're doing the fourth Taylor polynomial. So this is 4 times 3 factorial over 1 minus x to the fifth, which is exactly 4 factorial. So now we have all the data we need to do the fourth Taylor polynomial. So remember the value is 1 plus 1 times x minus 0 plus 2 over 2 x minus 0 squared plus 3 factorial over 3 factorial x minus 0 cubed plus 4 factorial over 4 factorial x minus 0 to the fourth. This is just 1 plus x squared plus x cubed plus x to the fourth. So you can see these aren't particularly difficult to calculate. It just, as long as you know how to take derivatives, you can find Taylor polynomials. Okay, let's try another example where we actually apply Taylor polynomials. So let's consider two functions here. Okay, so let's consider f of x to be e to the x and g of x to be 1 over 1 minus x. And let's see which function is larger near 0. So we're going to use Taylor polynomials to see this. So let's say let's use p2 of x to determine this. Well, we have to find the second degree Taylor polynomial for f of x first. So we can see these are just 1s each time because the derivative of e to the x is just 1. So p2 of x in this case is 1 plus x squared over 2. And we saw above, we can say this is the Taylor polynomial for g of x. We'll put a tilde over the top of it just to distinguish it from the Taylor polynomial for e to the x. And we just saw above that this is 1 plus x squared. So what this tells us then is that near 0, f of x, which is e to the x, is approximately 1 plus x squared over 2, and g of x, which is 1 over 1 minus x, is approximately 1 plus x squared. And we do need these, since we took our a to be 0 here, we need the x's to be close to 0 for this. And now observe that the first two terms of this are equal, but then after that you're comparing x squared over 2 and x squared. So we have 1 plus x squared is bigger than 1 plus x squared over 2. So that tells us then that 1 over 1 minus x is bigger than e to the x for x near 0. That's a nice, easy application of Taylor polynomials there. Now we're going to try a couple of more advanced applications that involve physics. So these are these ones you need a little practice to see how to do them, but they are examples of Taylor polynomials actually in action. So let's start with a physics problem here. So two electric charges. We have two electric charges of equal magnitude and opposite signs. So one positive, one negative. Okay, so if you have two electric charges of equal and opposite signs near each other, we call this an electric dipole. So let's say the charges Q and negative Q are a distance little r apart. So you'd say like here's Q, here's negative Q, and this distance between them is r. Okay, so these particles are going to create an electric field. Say at point P, a distance of r from the dipole. So big R is much larger than little r. So this electric field, EP, or say ER, because it's dependent on the distance r away, is given by Q over r squared minus Q over big R plus little r squared. And so our picture here would be like P is over here, and then we've got Q, and say negative Q like this, where this distance here is r, and this distance is little r. Okay, so let's take a second there for the setup. And as always, if you're taking notes, you can always pause to copy everything down to catch up. So what do we want to do with this? Let's use Taylor polynomials. To investigate Okay, so we want to use Taylor polynomials to investigate this electric field when we're far away from the dipole. In particular, let's show if r is large compared to little r, the electric field is approximately proportional to 1 over r cubed. Okay, so this isn't quite as obvious as ones we've looked at before on knowing what we want to do here. So once you see these a few times, hopefully you pick up how to do them, but it does take experience. So we're going to take the Taylor polynomials with a equals 0. But we want to figure out what is our x going to be here. So we want an x value x to be close to 0. Right, because that's where our Taylor polynomial will be a good approximation, since that's where we're taking our expansion. So let's note, since r is, say, much bigger than little r over big R is close to 0. So we'll take x here to be little r over big R. And this will be our variable. So now there's only, when we look at the formula here, when we look at the ER, right, if we look above, this is Q over R squared. And then we subtract Q over R plus little r squared. And now notice only this term has r and little r. And we want to take this and write it in a way that we have an x in there. So let's just focus on this term here for a moment. And notice if I want to write this with an x in there, I can write this as factor out an r, and I'll have 1 plus little r over r squared. And so I can think of this as q times big R squared, and I have 1 over 1 plus little r over big R squared. Again, you might not expect to know how to do this the first time. The idea is once you've seen a couple examples like this, then you have an idea of how to go about such a physics problem. So now we're going to look at just this term here. So let's look at 1 over 1 plus x squared. And we'll find the Taylor polynomial for this. Let's call this f of x. Okay, so let's make our table. So if you need to, pause the video, make sure you understand that these are the correct derivatives. Third one. Okay, and so we'll just stop there for this and just say the third Taylor polynomial then is 1, and then we had the negative 2, so it's going to be negative 2x plus, and then I have 3 factorial over 2 factorial, x minus 0 squared, plus negative 4 factorial over 3 factorial, x minus 0 cubed. So this is 1 minus 2x. Now 3 factorial over 2 factorial, this is 3 times 2 times 1 over 2 times 1. So this is just 3, or 3x squared, and I'm going to have minus 4x cubed. So now let's go ahead and use this. So remember, we had our f of x up here was 1 over 1 plus x squared. So this tells me 1 over 1 plus x squared is approximately 1 minus 2x plus 3x squared minus 4x cubed for x approximately 0. So that means if I plug in, I have 1 over 1 plus little r over big R squared is approximately 1 minus 2. Replace that x with an r over r plus 3 r over r squared minus 4 over r over big R cubed. And so now, continuing, remember the term we were looking at was a q over r squared times this. So that means q over r squared times 1 over 1 plus little r over big R squared is approximately q over r squared minus, and now we're getting a 2q r over, now we have r squared times r, so this is r cubed, plus 3q r squared over, now I have an r squared times r squared, so r to the 4th, minus 4q little r cubed over r to the 5th. Finally, we can put all this back together, so E of r, remember, is q over r squared minus q over r squared and 1 over 1 plus r over big R squared. And so this is approximately q over r squared minus, and now we use our approximation that we just figured out. And now notice this first terms cancel out, and then the negatives distribute through, so this is 2qr over r cubed minus 3qr squared over r to the 4th plus 4qr cubed over r to the 5th. So that's a good approximation for E, the electric field, as long as r is little r is very small compared to big R squared. But now we can say if little r over big R is very small, well, then these extra terms here, these are super close to 0. So and then in that case, E of r is approximately 2qr over r cubed, which is 2qr is 1 over r cubed. So we see then that ER is proportional to 1 over big R cubed. It is approximately proportional because we do have that approximation sign here. Just like we were trying to show. Okay, let's try one more physics example for this section. So one more instance of how we actually use these Taylor polynomials to simplify some formulas in physics. Okay, so we have van der Waals equation relates the pressure and P and the volume V of a fixed quantity of gas that's held at a constant temperature T. And the formula doing this is P plus n squared over A V squared times V minus NB is equal to nRT, where here A, B, N, and R are constants. Okay. So let's approximate P in terms of 1 over V up to degree, or let's say up to terms with 1 over V cubed. So again, we're gonna, so we will use here x, our variable will be 1 over V because this should be close to 0 as long as our volume is large. But now what we need to do to start this one is we need to solve this for P. Right, so if we're going to take a Taylor polynomial of something, we need to have a formula for it. So first step, if we divide by V minus N over B, I have P plus N squared over A over V squared is equal to nRT over V minus NB. And then I can just subtract, so I have P of V now is nRT over V minus NB minus N squared A over V squared. And now I'm trying to write this in terms of 1 over V, so note I can already write this as nRT V minus NB minus N squared A times 1 over V squared. So this term is kind of already okay. Already in the variable 1 over V. So it's the other term we have to deal with. So we're going to do the same type of thing as we did before. So let's take this term nRT V minus NB. And I want this to be in terms of 1 over V, so let's factor a V out of the bottom. So I have nRT, and I have V, and then I have 1 minus NB over V. So this is nRT over V times 1 over 1 minus NB over V. And now we're going to do the same type of thing. We're going to look at this term here. So let's look at f of x being 1 over 1 minus x. And we saw before that, say, p4 of this is 1 plus x squared plus x cubed plus x to the 4th. We calculated that above. We might have only done to x cubed, but it's the same step to do one more for x to the 4th. So that means that for x approximately 0, 1 over 1 minus x is approximately 1 plus x squared plus x cubed plus x to the 4th. So I can use that to say 1 over 1 minus nb over v is approximately 1 plus nb over v plus n squared b squared over v squared plus n cubed b cubed over v cubed plus n to the 4th b to the 4th over v to the 4th. So now let's go ahead and plug that into this equation above here. And so I get p of v is approximately nRT over v. Well, let's just put the equals here first. 1 over 1 minus nb over v minus this n squared a over v squared. And now we can put this approximation in. So this is now approximately nRT over v 1 plus nb over v plus n squared b squared over v squared. And we only wound up to v cubed, but we'll go ahead and keep the other terms here, even though we have more terms than what we need. Sometimes you're not sure how cancellation is going to happen, so you go a little bit higher than what you're asking for, and then you can always drop terms off if necessary. And so if I simplify this multiplying through, now I have nRT over v plus n squared r bt over v squared plus n cubed r b squared t over v cubed plus n to the 4th b cubed rt over v to the 4th plus n to the 5th b to the 4th rt over v to the 5th minus n squared a over v squared. And now remember, we only wound up to 1 over v squared, so we can say this is nRT times 1 over v plus n squared r bt times 1 over v squared. Well, we have to be a little careful here because we have another v squared term down there. So this is n squared r bt minus n squared a times 1 over v squared. That gets this term and this term. And then we only need the v cubed term because that's all we only were asked to go up to v cubed. And that's our approximation. And these other terms we just throw away because we were only asked to go up to v cubed. Okay, so these type of applications come up often. If you've taken an elementary physics class, you'll see this a lot where you'll have some formula for something in physics, and then they'll say, oh, it's approximately equal to this. A lot of times they only use the linear term, so it's only linear approximation, but you can in fact sometimes see where they use higher degree terms, and those are coming from Taylor polynomials.